Welcome to our courses on advanced power electronics and control. Today we shall continue with our power PWM rectifier, and thereafter we shall see some technique on the improvement of the power factor. So, we were discussing about the boost control. Now, let us have to see that there is a different kind of control technique to operate the boost voltage. Essentially, main function is that to maintain the output voltage most of the cases of the boost one. So, there is also a loop basically to maintain the voltage, that is called the outer voltage loop. We are not little bother about it. So, let us consider that there is an inner loop that will basically maintain that will basically deal with the current, that is called inner control current loop. What happened here actually, there will be a current sensing resistor, or you can do it with the Hall effect sensors at present case, and this is essentially a PI controller. So, is a practical PI controller, integration and parallel path, and you have a current reference that will be actually compared. Then this value of this actually error del I is been fed to the compensator. Generally it is nothing but a lead lag compensator, depending on your faster response and all those things. We have to have a gain margin, phase margin of actually the system in a desired level. So, this compensator essentially will do that, will give you a desired gain margin and phase margin. Thereafter, there is a pulse width modulator. That pulse width modulator basically generate the gate pulses, and ultimately you require an isolations, because pulse width modulations is a very low frequency, and sinking out the current for the gate drive is not allowed. For this reason you require buffer to run high impedance mode. This is the one of the way to basically operate your boost converter, that is called actually average current mode. You can have another mode called the peak current mode. There actually you, instead of you allow to current to boost up in a peak current mode, and there also its own advantage. Each has its own advantage. Is essentially if you go by the stability analysis will be quite easy, because you have a compensator ensure that actually does not go out of the system, go out of the stability. So, see that how this concept can be incorporated in a actually PWM rectifier. So, essentially you have a rippled DC here in your output. So, so ultimately you will have a VT control, and you got a multiplier. So, you generally what happen you instead of this you generate a sinusoidal OF. Basically it shift back this waveform in this part. Thereafter what happen, most of the cases you will sense this current, and you will sense this current, and ultimately you will convert into the actually voltage by multiplying with the effective value of the resistors, but here in this case it will be an op amp will give you the gain, and ultimately you get a VA. Please note that actually you want actually this waveform, and you want that current to also follow this waveform, and thus in input side current will be something like that, will be contaminated with this envelope. So, thereafter generally you have one block, generally you have a hysteresis block, generally that will generate the hysteresis band, and thereafter you got a compensator, that is essentially a lead lag compensator that will ensure the stability of the circuit. Thereafter PWM, again the pulse is generated. I ask you to actually student to refer back our practical power quality improvement boost type converter, and there is, and this generally this whole system comes under a single package of UC 5854 or 555 or so on. So, what is the basic Features of this PWM technique: current reference is received from the input voltage waveform. Multiplier allows control to evaluate as a resistive load. So, actually it will make it voltage and current almost is in a same phase, and compensation of the current loop is employed by this basically a lead lag compensator to have a faster response, actually low overshoot, all those actually desired feature. Generally gain margin we require to keep around 75 to 60 degree. So, phase margin also actually we require to have a stability point of view, we require to have something. So, these all those tuning has to be done by this compensator. Now, actually we shall see that how does it operate practically. The current sensor has a gain RS. So, basically it has been multiplied, we have a scaling, because most of them nowadays we use LEM kind Hall effect current sensor resistors. So, that is actually VAT RS actually into multiplied by this actually this IG. Then loop is designed is such that VA is almost equal to VR, and multiplier will ensure that VR equal to K into VGX. So, Kx is basically a multiplier, and that gives you basically V equal to IR kind of relationship. Hence, it evaluate the characteristics of the resistance. So, you can see that effective resistance of the circuit RE equal to VG by IGT equal to VR Kx control X by VA by RS. So, ultimately you can make this is your effective resistance comes into the picture, and this can be simplified. So, this term, and since if you say that VA equal to VR, so this term and this term will cancel, ultimately you can write that RE, that will be basically the function of the control voltage. So, that will be basically RS by Kx into V control into T. So, RS is again mostly it is fixed, and so by controlling basically the control you can get a sinusoidal pattern into the input of this rectifier. So, see that actually if you have a transformer kind of model actually input and output. So, you have a effective RE and power will be transferred to the system. So, RE will be basically RS by Kx Vs control, where you apply the control in such a way that it always sees sinusoidal current in the input of this rectifier irrespective of the load as well as the change of the source disturbance sometime. So, current control waveform. So, this is the something we require to like to take an example. As I told you, actually task of this converter is essentially to maintain the voltage here constant. So, for this reason I was telling few slides ago that there is a outer current loop also. So, you have a voltage and it has been scaled down. By scaling down you got a voltage reference. Thereafter it has been multiplied by a scaling factor, or it has been filtered out by a filter to actually suppress the high frequency noises or the ripple that will be there, and ultimately this voltage will be fed to this actually Y. And same way this actually the rippled DC, that is basically VGT at this point. Please mind it, basically this rectifier does not have a capacitor in the output, thus we have a rippled DC. So, that will be multiplied and you get some reference voltage that will be actually compared with the reference current multiplied by some constant. So, ultimately the current flowing through this part is there is a input current to this boost converter. So, it will be convert, and ultimately this comparison will gives you the error. Generally error has a error processing block fitted by a saturator. So, that actually you control over the duty cycle, because you know that the control point of view there is a limitation on the duty cycle. So, generally we cannot go beyond 0.66 theoretically. So, this problem is there for the boost converter. So, for this reason actually we have a limiter followed by a compensator that will basically give you the shaping of the gain margin and phase margin that will make the system prompt and you not allow go to the out of the control loop, and all those issues will be actually addressed here by the lead lag compensator. So, thereafter actually you have a pulse width modulator. Pulse width modulator essentially generate the pulse, and thereafter you got a high impedance state that will actually drive the MOSFET or IGBT depending on your power rating. If the power rating is low, then generally this solutions within a 500 watt or something, this solution comes out with the MOSFETs, and if the power rating is higher, then we require to have a IGBT solution, and if you have a huge power rating around more than 10 kilowatt, then we may require to operate actually this boost converter in parallel, and there are many topology like interleaved boost converter and all those things. So, these can be incorporated according to the rating of the system. So, let us understand how does it work. The feed forward is sometimes used to cancel out the disturbance of the input voltages. To maintain a given power throughput P average, the reference voltage V ref 1 should be P average into V into RS by V square G RMS. Now, what happens, this is that this point voltage is actually V square G. So, you have a peak detector and you got Vm and you got a multiplier. So, ultimately this output and this ripple voltage will be multiplied and will detect the peak. So, accordingly you can adjust that whether there is a sag or swell, something like that, and accordingly you actually you get a value of basically kV xy by z square. That essentially will set to the reference current. So, ultimately it will be compared with the VA. So, this will be a current sensing resistor or Hall effect sensors, whatever may be, and then this is a actually PI controller. This part basically integrate, and this part is proportional, and generally it is required to put a small resistance in theoretically to have a bandwidth of the system. Bandwidth of the system which will be related to the switching frequency of this actually the MOSFET or the IGBT driver. So, generally in practical cases, most of the cases if you use IGBT, then frequency is restricted in around 5 kilohertz. Then actually you can take this RC bandwidth as basically 1 by 10 kilohertz, that is actually 10 microsecond. So, you can do in that way and calculate the actual values of RC, and this gives you the gain. So, how much scaling you require, because and this actually sum up the effect, and thereafter you got a comparison, from there you got a compensator, from there compensator will basically gives you the stability and the promptness, same way as I told you there is a PWM and it will work. So, this is the overall control circuit of the boost type PWM rectifier. Now, so actually there is a feed forward control, please understand that. Generally feedback control gives the stability, but feed forward control gives the promptness, fastest in action. So, feed forward control is been produced by this reference. VRF1 equal to KV control into VGT by Vm square. So, this is the actually the feed forward control block, and the average power is then given by KV into V control by 2 into RS, where RS is the effective value of the scaling resistor. So, in this way this is actually used for control. Now, we can go for the small signal analysis for analyze the stability of this boost control converter, PWM boost control converter. Now, it is a average model. So, any phenomena less than 10% of its switching frequency can be captured here, and this is called small signal model. So, what is the essential part of the small signal model? We give a perturbation in and around basically, since the system is non-linear, you have a switching, you have a on and off states. So, we give a perturbations very close to the operating point. Then we see that what kind of actually how this system will behave, and this is called average modeling. So, and by average modeling we can capture the phenomena and stabilities which is actually 1/10 of the switching frequency. So, we give a perturbations Vg with Vg delta, similarly you have a perturbation dt delta, and all gives a given a perturbation, all the parameters, that is I Ts, Bts, V1. Please note that what are the, this is basically the input current I1 Ts, this is basically the voltage across the switch is V1 Ts. Similarly, current in the model secondary basically V1, V2, it is something like transformer. Why? Because if you assume that switching losses or other losses are 0, input voltage into input current should be equal to V2 into I2. So, it is something like a step up transformer because energy conversion holds. So, for this reason we will have these values. Now, problem of this actually this present is the variation of the Vg, because input voltage can vary because of the sag and swell of an I, variation in Vg, I1 and D are not small. So, you can have a huge variation of this. So, we are faced to design a control system that exhibits significant nonlinear time varying behavior. So, this is something quite trivial, actually load may change, sag may occur. So, that basically not restricted that these assumptions. So, that system becomes little complex. Now, let us see that how can we operate it. When rectifier operate near to the steady state, then we can say that actually we have given a very small perturbation or disturbance. So, Bts will be actually the Bt, that is the actual value, plus delta Vt. So, we say that actually this mod delta Vt is much less than this actually the mod Vt. In this case of the boost rectifier, it is sufficient to linearize these equations for the average control. So, we can linearize it. So, we differentiate it with its neighborhood of the capital V. So, V L di dt equal to Vg minus of this differentiation. So, we substitute it, you get actually these values of V delta and D delta. Thereafter, we can get actually L di dt equal to this value. So, the term much smaller than the linear AC term, hence it can be discarded and we can basically this values, because it is a variation of D and variation of del V. This quantity is also small and this quantity is also small. So, thus we can neglect this smaller quantities and ultimately you can discard this equations comes out to be this, and thus your circuits, equivalent circuits, you can write IGS by DS equal to V by SL. So, you got this kind of circuit, so where it is multiplied by dt into V. So, this becomes the equivalent circuits. So, the previous approach is not a sufficient to linearize, that is what I am telling. Linearize the equation, need to design the rectifier average current control of buck boost, choke, SEPIC and other converter topology. These are truly non-linear time varying system. So, we will come later. An approximation approach is sometimes used. These cases are the quasi-static approximation. We will come to the quasi-static approximation now. Assume that the AC line variations are much slower because your switching frequency is in a range of the tens of kilohertz, whereas your supply frequency is 50 hertz. So, any change in the basically the switching frequency, any operation in the range of the switching frequency, with respect to that we can suitably assume that the sinus, even though it is a varying sinusoidal wave, is almost constant within the short duration of time. So, that is called quasi-static approximation, and we can find the slowly varying equilibrium duty ratio. That is whole about it, because this is the phenomena, this is 10 millisecond, and so and your switching frequency is of 10 kilohertz, that is when it is actually 100 microsecond. So, it is if it is 100 microsecond. So, what will happen, actually within a actually it is 10 to the power minus 3 times of it. So, within that 10 to the power minus, actually if you can consider that within the actually 10 to the power 100 microsecond. So, you can assume that this value is linearized and this value is almost DC. In the literature, several authors have reported a success of using these methods. So, you can refer to the actually the paper and the data sheets of the active boost rectifier. So, you can find many reported journals. It should be valid to provide that the converter dynamics is sufficiently fast such that converter always operates near to the assumed operating points. No good condition on the system parameter which can justify the approximations is presently known for the basic converter topology. It is well understood that the field of the control system that when the converter dynamics are not sufficiently fast, then the quasi-static approximation yield neither necessary nor the sufficient condition for the stability. So, if you increase the switching frequency of the supply, then quasi-static model may not actually predict your stability and other condition according to the control system. Such behavior can be observed in rectifier system. Worst case analysis to prove stability in a stability should employ by simulations. So, you have to do the simulation and find it out that the system is stable or not in a worst case. Now, the control of the current waveform, this is something we require to understood. So, current controlled another way of actually monitoring, we have seen the average current mode control. We have also another mode of control, that is current program control. So, what happened, you got a VG, that is a ripple DC coming from the rectifier, your boost topology, essentially you sense the current by CT or a LEM sensor, and what happened here, you have VT control and you will get an input. So, you get multiplier. So, you got basically essentially ripple kind of thing. So, thereafter mostly what happened, this control can be also positive or negative. So, make it this current like this, some chip uses that. So, then what happened, you actually then sense this current and ultimately you have a feed forward ramping block. So, what happened here, you basically ramp on the current and it will check basically the clock pulses, and so you will take an input of IA for this interval of time. This is basically a time integration, thus actually it will vary. So, ultimately it will add on. So, this current and this ramp on basically will be compared with the reference current that will be set by essentially a kx into Vg So, that's current is a compensating current IC, then it will be compared with an op amp, and when this current actually rises above this, or there is a pattern, it try to cross this pattern, then it will reset the clock, thus the output of the switch will be off, again current will come down, again same cycle will be repeated. That is called control current waveform mode, and you have inherently done the short circuit protection here. That is one of the biggest advantage of it. So, you have a ramp control, and thus you got a short circuit protection. Sometime it is also called the peak current mode control. The current program control is a natural approach to obtain the resistor emulations. So, assume the system is connected with the resistance. The peak transistor current is programmed to follow the input voltage, which is rippled in nature. The peak transistor current differs from the average inductor current because of the inductor current ripple and the artificial RAM added here. This leads to the significant input current distortion. So, for this reason we require to plan it accordingly. So, this distortion with sometime actually leads to the malfunctioning of these devices, but there is a two advantage of the system. We shall see later that actually this reduces the order of the system. Ultimately, if you have a second order system, it can be underdamped, overdamped or critically damped, but if you have a first order system, it is naturally damped. So, for this reason you have a added advantage here. So, this IGT what you are talking about may have operated in a CCM mode or in a DCM mode. So, this is the value in case of this actually in DCM mode, that is ILC square F Vg minus this thing, and in case it is in CCM mode. So, value will change by this, and CCM boost converter will have this boundary condition. So, IGTS should be more than, to be in a continuous conduction mode, is that TSV by 12. This is something like the system parameter, you have chosen the switching frequency, the supply voltage and Vs, Vg by V and 1 minus Vg by V, or we can approximate like this. So, it is desired that basically IC should be actually Vg by effective resistance Re, and multiple slope compensation MA essentially we require to figure it out like this. So, that value MA which we are setting, that will actually, otherwise it will lead to a distortion. So, these we will try to compensate the continuous mode of operation. Ultimately MA will be V by 12. As we have seen the previous case, same way, this is the contour of the DCM and this is the control of CCM for various values of the RE. Now, when actually it is quite low load, so actually we will find that it will go to this actually CCM mode at this point of time, where this ratio Vg by V will be close to 1. So, for this reason operating this actually in a conditional continuous mode for the low load is extremely difficult. Gradually when you have a very high load Re equal to 0.1 of the R base. So, there what you can find that actually you have a almost continuous conduction mode started, and you will find much easier to operate, and R base is essentially is the 12 by Ts. So, there this is the value of the R base. So, this is the characteristics of operations of the CPM board boost converter characteristics. So, we shall continue with the PWM rectifier and some technique on the power factor corrections in our next class. Thank you for your attention.